So in recent years, there's been a bit of a revival of cyclic universes. In the book Battle of the Big Bang, we cover many of these newer cyclic theories, but can they actually be eternal into the past, or must they have their own beginning? Well, a new paper claims to have an answer to this question. And today we have the authors, Petar Pavlović and Marko Sossich. Welcome, guys. How are you doing?
Hi. Nice to be here. Nice to be here with you, and everything's fine. Yes. Yeah.
Good. Well, I'm super excited to talk about your paper. So why don't we start? Well, there's several versions of a cyclic universe, but your paper, I think, focuses on the traditional version where the universe expands and contracts, expands and contracts. Can you tell us a little bit, Petar, about the history of these models? Where do they come from? Why have they been revived in sort of more recent years? What's the motivation?
What is the main motivation? And it was a historical motivation for the emergence of the idea of the cyclic universe is the problem of singularity. So somehow this is contrary to what we would like to do in physics. We would like to describe the whole reality in a consistent way. And if you have a singularity, that means that you have failed in this task. So actually, the first model of cyclic universe dates back to the 30s. So by Tolman. So it was almost as old as the Big Bang theory. And this first version was completely based on Einstein's general relativity, and it assumed a finite universe. So the universe with a positive curvature being shaped like a sphere. And then it had actually many problems still. It was eternal in a sense. It was oscillating eternally, but there was still a singularity. So this first motivation was actually not then completely realized within the model. And the second problem was that this radius of the universe, because it was a finite size, was related to entropy. And so it was assumed that entropy increases with every cycle. That means that the radius needed to be smaller in the past. And then eventually it needed to actually converge to a point. But those are some of the first problems. But I think what inspired this new emergence of cyclical universes in the past decades is the new shift towards the modified theories of gravity. So actually, we don't know what is the very precise form of the gravitational equations for high energies. We standardly work with Einstein's equation, which is just one possible type of field equation for gravity. So although Einstein's theory of gravity is consistent theory and has many interrelated assumptions, this form of the equation, its mathematical form, is a different question. And so Einstein chose a very specific assumption that could lead to a Newtonian limit. So, but then after 98, and that the accelerated expansion became a relatively well-established fact, there was this new focus on modified gravity theories in order to explain the so-called dark energy, not as a new form of unknown substance, but as a result of modification of gravity, which is reasonable because there is enough of mathematical space, so to say, in general relativity to try to do so. So then, when we move away from the traditional Einstein equation for gravity and consider the modified versions, or like even string theories and this approaches to unification of gravity with quantum physics, we have much more freedom to mathematically obtain cyclic solutions. So I think that was one of the main reasons for the revival of cyclic cosmologies in the last decades.
Right. And Marko, so Petar hinted at some problems with entropy for a cyclic universe. Can you explain, like, what are these problems? Why would they be an issue for cyclic universes?
Yes. Firstly, we know that entropy is associated with the second law of thermodynamics, which is one of the most important physical law today, we know. But we must be aware that second law of thermodynamics is also a statistical in its nature. So when we are talking about the cosmology and the universe as a whole, then it's very important to see how these dynamics and the statistical mechanisms are associated here to these dynamics. And we know that entropy from the second law of thermodynamics must always increase in the future from the past. But as Petar said before, one of the first cyclic universes was associated with Tolman, and he saw that when we are going back in history, we need that as entropy always is growing, then in the past, entropy probably goes to zero. And in the future, the entropy, and we are talking also, we must make a distinction between entropy and entropy density. We see that entropy density could blow up in the future. And we now must find a way how to circumvent these problems in the cyclic model of universe. So we also have a problem, the question of entropy at the Big Bang. We know that if in a thermodynamical equilibrium, as was in the Big Bang, a big soup, we call it, the entropy was maximum. So how now the entropy is growing when we have a maximum amount in the Big Bang? Some of the solutions are the black holes, which are objects with a higher amount of entropy, which are creating at the future. But this notion is based on the new formal definition of entropy, so-called Shannon entropy. So there is a highly hypothetical distinction between Shannon entropy and physical entropy, the second law of thermodynamics, and how to impact all these problems together is also a new question we are now dealing with. So these are the things as I see the main problems of entropy. This growth, which goes to the future and blows up at some point and also back into the past.
Right. So to summarize, basically, if the universe was eternal into the past, how is it that we're not in a maximal entropy state now? Well, we're clearly not. And then the other problem is, how is it that the CMB, which looks like a thermal black body, that looks like very high entropy, as high as it can be? So
Yes.
how is it that then we're not in this maximal entropy state? Also,
Yeah.
a cyclic universe has a problem and a Big Bang universe has this problem, right? Petar, why don't you tell us how cyclic proponents, I mean, I'm thinking in particular, like one very popular version of the cyclic model now, well, I don't know how popular it is. I shouldn't say how popular it is. Paul Steinhardt, Anna Eas, they've been advancing a version of a cyclic universe that expands and contracts, and maybe there's maybe dark energy is not a constant, maybe it changes over time, so this would allow it to recollapse. So that's a popular-ish version of the cyclic universe. How have they proposed to sort of get around this entropy problem?
So actually, the big problem with entropy and cyclic cosmology, it happens at the phase after the turnaround. So not the expansion, but the contraction phase, where if the cyclic universe is symmetric, then you actually have a very asymmetric type of behavior with respect to expansion, because now the matter and energy is not getting diluted. So parts of matter and the structures are not going away from each other, but they are actually falling onto each other. And this brings a very sharp increase of entropy during the contraction cycle. So this is the problem in general with these models of the Tolman's type, the models which are symmetrical with respect to expansion and contraction. Those two phases are symmetrical. So basically, the standard solution is that one needs to understand the difference between the entropy and the entropy density. The entropy always grows in the universe, but the entropy density can actually decrease although the entropy increases. It can decrease if the universe actually expands fast enough between the cycles. So essentially, the idea is that you don't just have oscillatory behavior in the cosmological evolution, but you have oscillations which are mathematically combined with the growth of the scale factor. So the amplitude is growing between the cycles. And in such a way, entropy density is decreasing in the universe. And actually, in the parts of the universe which are causally connected, then the observer can measure that the entropy, which is his observable entropy, is decreasing, although the total entropy of the whole universe is increasing. So this is very interesting type of models. If you bring the asymmetrical type of oscillations which grow in amplitude, then you can essentially solve this problem because you dilute the entropy and its density. No, so this is important proposal, and also we have showed earlier in some papers it can be connected with some other issues like magnetogenesis problem. How were the magnetic fields, which are so universal now in the universe, created? One option can be that actually there is a secret universe which is asymmetrical, and then from some small seeds, electric fields existing in the contraction phase, they can be amplified.
Right. Okay. So, Marko, this picture then of solving the entropy problem by having each cycle has to be bigger than the next one, right? So then you can dilute the entropy and you're not faced with this problem. But it's been argued that it falls victim to a theorem called the BGV theorem. Can you explain, what is this theorem? How does it work? And then why a cyclic universe is said to fall victim to it?
Yes. So the BGV theorem from both Gut and Vilenkin, those are the names they stated. They proved this theorem. In fact, it's a very general theorem in cosmology. It states that if we have an expansion rate of universe, it doesn't have always to be the Robertson-Friedman metric or a homogeneous or isotropic universe. It can be a little different universe, but if it has some expansion rate at every cycle, then it means then the Hubble parameter it's greater than zero. And in this sense, they proved that every universe, from a purely kinematical perspective, must have an past incomplete geodesics from this H, or we call it Hubble parameter, when it's greater than zero.
Explain what you mean by a past incomplete geodesic. I'm not sure everyone will know what that phrase is.
Okay. We know that every particle must move. So when we say that particle must move, if we are going and saying that the universe is eternal, we know that the particle always must move. It doesn't have any sense if we call it that at some point that this geodesic, this particle stops. In fact, it's nothing. So this nothingness, what happened in the past, we call it this past geodesic incomplete.
So we could say maybe also to give a picture. First, we could imagine geodesic like it's just a free sliding without any exterior influences, without any friction. You are just sliding on some curved space-time. And then the question is, if you can extend this path in the four-dimensional space-time of this sliding before and before and before, and if it happens that you hit the wall somehow, that you cannot extend it, like if you are drawing a line with a pencil and then you come to the end of the table, then you cannot extend this line any longer. Then we talk about geodesical incompleteness. And this is a signal of a perturbable singularity, but it is, as we will talk a bit later, not necessarily a singularity.
An important also here to say is that it does not depend on the Einstein equations. So the general relativity that was made by Einstein, it can be any modified theory, but at the purely kinematical level, if the expansion rate is greater than zero, then we always hit this wall at the past. This is the main result of the BGV theorem.
Right. So why does that mean that this expanding, well, I guess we're going to answer the question pretty straightforwardly. This expanding cyclic universe then is going to fall victim to this because each cycle is bigger than the next one, right? So therefore it's expanding over its average history and therefore would be past geodesically So we'll hit this wall. Is that right? Have I got that right? Is that the argument?
Yes. That's the logic behind it.
Yes.
Right. Okay. So Petar, before we come to your potential solution, I noted recently there was a paper by Lesniewski, Essen, and Davis, and they've actually challenged this BGB theorem. Can you explain, like, what was their challenge and what are your thoughts on this? Do you think this is a valid challenge or not? Or...
So actually, I think it's a valid approach. It's a standard approach. When you have a theorem, then you construct monsters. So you try to find a specific construction that shows like a counterexample. And this is essentially what they did. So it is a general attack on the theorem by constructing a specific counterexamples, and it is not constrained or necessarily related to the issue of cyclic universe and so on. But in general sense, it shows the mathematical limitations of the theorem. This work by constructing some monsters. And actually, essentially, what is the problem is that in its original form, the theorem was not very mathematically precise in the sense, what does it mean to have like significantly decreasing scale factor in the past and so on? So you need to mathematically consider some limiting procedure, and you need to be very careful how you take this limiting procedure into the past. So you need to consider the time is going to negative infinity, and then what happens then mathematically. This was not very precisely dealt with in the original formulation. So there, in this limit, you can actually create different sorts of behaviors, and actually you can find the loopholes there, and you can evade the theorem. That was the basic logic in this.
Is it right to say something like there's different? You have to assume in the BGB theorem that the average expansion is positive, but there's different ways to calculate that average, and they found a way to calculate that average that sort of violates the theorem.
It depends how you define the average. Yes, the definition of average is very important, and also, sometimes it is said it needs to be positive or greater than zero, but this is the very interesting part. Is the average Hubble rate equal to zero or greater than zero? Because if it's equal to zero, then at this very point, the theorem is actually not well defined. And this is the critical point of the whole thing. So there are many issues. Basically, they are all related with problems of mathematical precision of the original formulation.
Right.
And the point is, I think, when you try to be very mathematically precise and you make this theorem you put it in a very strict language and you consider the limiting procedure properly, then this theorem is no longer as strong as it was in this, so to say, more rough formulation. And there are many loopholes there which are opened by this.
Right. Actually, can I just probably one last time on this? It seems hard to imagine, like, if the universe is just expanding forever, in what way could the average not be greater than zero for the Hubble parameter, which describes, the expansion of the universe? It's hard to imagine for a layperson how it could be anything other than something bigger than zero.
But the important point here is to consider what is happening with the expansion when you go into the infinite path. This is, if you go further and further into the past, what is happening? So that is the important question, how the expansion is looking like when you are going into the past. And then this needs to be precisely defined, because mathematically you can have expansion going on and going on and going on, but if you consider the limit of going into the past, then this rate of expansion approaches zero, for instance. And then you can actually escape falling as a prey to the theorem. So the point is, it's just the matter of mathematical precision when you take the proper limit of going to the past. And there you need to be very precise. And these are all technical matters. So it's not very much possible to see all the details just with words. You know,
Right.
you take findings and be very precise what's going on in terms there.
Right. Okay.
Then we have these so-called monsters. They're really artificial objects mathematically to see how to circumvent or to go away from the BGV theorem. The important fact also is the asymptotic behavior. This is the most important part of the BGV or this by Davis and Eason work to see what is happening into the past. This is the crucial part, that we have a constant scale factor into the past, and this is the way how we can find this loophole in this.
If you have a scale factor which is growing in the future, but in the limit of the infinite past, it is going to a constant value, that is a mathematical possibility, then you will have asymptotic value for the expansion rate when you go to the infinite past equal to 0, and then you easily relate it to.
Right. And just to explain to the audience, the scale factor is like a measure of the size of the universe compared to some other point in time.
Yeah.
Is that right? So that's what we mean when we say the scale factor. So if the scale factor is very large, the universe has grown more compared to some previous time. So let me come to you, back to you, Marko. You talked about geodesic incompleteness, and that's what the BGV theorem shows. Is that the same as we hear this phrase singularity? We think about the curvature going to infinity and the density going to infinity and the pressure going to infinity. Are these the same things? Are they different? Does one imply the other? Can you just unpack that difference before we come on to your paper and how you might evade BGV for a cyclic universe?
Yes, it can be, but not necessarily, as I am aware of that. When we are talking about singularities, we also are talking about some strange geodesics and hitting also some walls. But these walls can be a physical singularity, and this means sometimes that the Einstein equations, the main equations of the dynamics in cosmology, will have some infinite values. Similarly, like we are talking about Coulomb law, for example, we have distances which the force is growing, and at the point 0, the force is blowing up. The same happens when you have some singularities, space-time singularities, then the equations blow up. They're infinite. But when we are talking about geodesic incompleteness, we can imagine that the particle is going back in time, and also the energy is growing, but then we cannot talk about classical trajectories in these regimes. Maybe some quantum effects came into this part, some interplay between quantum and classical. And in this sense, when we are not talking about classical trajectories, we cannot make that it is the same as the singularity and the path of the particle in the same sense. So it is not necessarily the same thing.
So you can see there are some geodesics which are incomplete in the past, but there is no physical singularity actually. So such type of solutions are also possible. We should mention that there is this paper wrote by Prokopec some time ago, which discusses just this central issues, that actually geodesical incompleteness does not necessarily imply singularities. This is a very important distinction. You can think in simple terms of it that actually geometrical incompleteness is a very technical notion. It is just something very mathematical and technical, and singularity as a physical singularity is something conceptual. So there's actually two levels of understanding. Sometimes geodesical incompleteness can signal that there may be a physical singularity, but it ain't necessarily so.
Right. So let me just ask the question then. Imagine I've got a universe and you tell me this universe is geodesically incomplete to the past, but it has no singularity. Do I understand that universe has a beginning or doesn't have a beginning? Or can I not tell?
No, the question of beginning is actually this physical conceptual question. If there is no physical singularity, so all the solutions are regular, and for instance, you can always extend the solutions in the infinite past so that you always have a sort of behavior, then there is no beginning. It can mean, for instance, that you have your trouble with some geometrical description or mathematical details of the formalism, which is not giving you geodesically complete solutions. But that can be just a technical issue that you can resolve, and still you can have the complete, actually, infinite universe without beginning.
Right. So, but if I knew that it's geodesically incomplete, could it be eternal into the past, or is that just a statement? It's incomplete, therefore it has a beginning.
In principle, it can be infinite in the past.
Okay, even with
physically complete, because the geodesical completeness does not necessarily imply that there was a physical singularity. And when we are speaking about the origin of the universe and so on, we are actually asking ourselves, is the physical singularity necessary or not?
Right. Okay. So let's come on to your paper. So basically, let's just summarize the picture. We've got these cyclic universes, they expand and contract, but there's this problem with entropy that can be solved if the entropy density is declining. So each expansion has to be bigger than the next one. But then if we go back to the past, they're getting smaller. That gives us this picture that looks vulnerable to the BGV theorem. Now, you say you've got a construction that actually allows the universe to be eternal into the past and solve the entropy problem in this way, but yet isn't vulnerable to the BGB theorem. How do you do it?
Okay, so basically, first, we wanted to somehow model the growth of entropy, because mostly these arguments are purely qualitative, but we need some sort of mathematical model for the entropy growth. And this is what we try to propose, a very simple model of entropy density, and then how is this actually evolving between the cycles. And then we show by the computations that, of course, you can have entropy density decreasing if you have the universe expanding with higher amplitude between the cycles. And then when it comes to the past and the BGV theorem, you need to be very strict and precise. And there you can find a loophole in the BGV theorem, and you can consider, for instance, the type of solutions which have the asymptotic. That means when going to infinity, value of the expansion rate going to zero, not being greater than zero, but going to zero in negative infinity of time. And for these solutions, this theorem, when taken with appropriate limit, is actually not, it cannot be applied to such situations. So for that types of models, which have somehow restricted behavior in the past, it is restricted in the sense that Hubble expansion, the average expansion rate cannot be greater than zero, but it needs to somehow approach zero when you go more and more into the past. You can have the BGV theorem, you escape the BGV theorem, and at the same time, this universe is, when you move to the future, growing and growing by each cycle, so the entropy density is decreasing more and more. So you have those two things solved at the same time.
Yes, importantly, the entropy is always growing, so only the entropy density is decreasing to make this distinction, which sometimes they think that is the same thing, but it's not the same thing. And also the critical value was this past function, so we try to find sometimes very complicated functions, but not always. Sometimes it was easy to make this constant and find the asymptotic behavior, try to make this loophole meaningful, and then the same thing what happens with similar thing what Stein had proposed in the future goes pretty much the same thing, but only the functions are a little bit different in this case.
So one could say it's actually just a small type of a modification to standard solution. And just to show how simple it can be, for instance, a large solution is if you have a standard type of a solution and you just add a positive constant to the scale factor. And believe it or not, adding a positive constant to the scale factor actually changes completely the behavior of the scale factor in the infinite past. And then PGV theorem cannot be applied anymore in this condition. So if you just take some well-known solutions proposed for the evolution of scale factor, like standards, and you add a positive constant, that can be enough actually to have a valid model. So it can be very simple type of a modification to escape the crutches of BGB.
So when you say add a constant, I mean, we're familiar that Einstein, when he came up with his theory of gravity, he added this cosmological constant. Are we talking, help me have a physical picture of what it means to add a constant. Is it something like that? What are we talking about here?
Yeah, it is just a kinematical constant. So to say, imagine the problem of the moving body, for instance, moving with constant velocity. So you can say that a body starts from position equals 0, or for position is equal 10 meters with respect to some origin. So it is that type of change in the scale factor. What is so to say, the minimal value of the scale factor? Is it going to 0, or is it going to some value higher than 0? And we are just talking about this. So it is actually physically insignificant. It is not like addition of a constant in Einstein's equation, something which Einstein did, which has large implications. This is just changing the description of the scale factor evolution. So it is just a kinematical type of a constant.
Yes, when this is this new approach in the asymptotics in the infinite past, but the real question is what matter could support this constant we are talking about.
Right.
And this is the new important question that we do not solve at this time. Any modified theory can add this constant. It's not a problem. But when we are talking about matter, the point is how, what is the dynamic of this new matter that can add this constant and taking it always to the past and find. So this is
what is maybe essential. What is maybe essential here is that for this to work, you need some extension of the standard Einstein's equation. Like you need for standard and so on. You cannot just take the classical Einstein gravity and then have cyclic cosmology which solves these issues. This is not possible. So there is some sort of modification needed, and this modification then should enable these types of solutions. So we in this paper, we wanted to stay as general as possible, just to address the general matters. So we don't go into constructing this or that model. We just show such models are possible and that is not actually difficult to construct. They're just like the modified gravity theories which are existing now on the market at this time.
So let's just help me have a picture of this universe. So if I had the previous construction due to Steinhardt and his collaborators, we've got a universe growing, it's expanding, and then it contracts, then it expands again, but the expansion is bigger than the previous one. As we go back into the past, it's smaller and smaller. So with your added feature, what would it look like? So help me visualize this universe.
Actually, it's the point is that it's basically the same. It's basically the same. It's the same type of behavior. It's the expansion. It grows and grows by each cycle. The only difference is when you go to the past, the expansion rate is going to 0, or scale factor. If you go to the past, it's going to diminish more and more and more, but it's not going to 0.
Yes, right. So basically,
constant value.
It's something I've always wondered about the entropy argument. Is that the idea is that, well, if the entropy is increasing into the future, then if we go back and back, it must get to 0. But I've always wondered, well, why couldn't it just get smaller and smaller and smaller and never get to 0? Is that essentially kind of something similar to what you're saying?
Yes, exactly.
Similar, but in kinematical terms, yes.
Right.
Because this is just kinematical to escape PGV. So it's getting smaller and smaller and smaller and smaller. The scale factor, not the entropy we are talking about. The same logic, getting smaller and smaller and smaller, but never going to zero. And this is actually the crucial point, because then BGV can do nothing to you then in this, with this evolution, because this is the very loophole of the whole theorem.
Right. So Marko, can this solution be applied to inflation as well? Originally, the motivation for the BGV theorem was that inflation is thought to be eternal into the future. The authors asked, is it eternal into the past? And they said, well, no, it's only eternal into the future. But could you use this sort of construction to say, within inflationary model, within eternal inflation, that could be eternal into the past, or is this only relevant for the sort of cyclic scheme of Steinhardt?
The answer is yes. We can construct as many as models as we like with this trick, let's call it. We also, in our work, we made a function, an interesting function that is similar to inflation, so exponential growth, but at some point it has some fluctuations, some oscillations, yes, at some time. But looking this at the whole and shrinking the time interval as we like, so changing the parameters there, we can make this very, very small in time and have the description of inflation at a particular time at the cosmologies. So the answer is yes, and we have it in our work we published.
But the other problem is, and we did not look into that, because actually we are the proponents of the cyclical models, we are not so much maybe concerned with inflation, is the other question is if the viable models of inflation can be of such sort. So if you can have enough of e-folds generated of inflation and so on by this type of model to fit all the empirical data, that's another question. This answer is just on this basic theoretical level, just in principle.
Right. And we should explain to the viewers that, generally speaking, cyclic models are proposed as alternatives to inflation. So, some people don't like some of the implications or some of the assumptions of inflation because they've constructed cyclic alternatives. Is this just something arbitrary that you've added on to find a loophole? Or is there any sort of physical motivation? As you mentioned, modified gravity theories. Do they give any sort of motivation for this sort of picture, or is it just let's see if we can find a loophole?
Who will answer?
Marko, go for it.
Okay. So the motivation, firstly, is to find a theory which, of course, does not have these singularities, these problematic notions in standard gravity. Also, one of the motivation was to find a way to cure these possible cyclic universes, which was very strange that we cannot find the solutions, the BGV theorem, the new works that try to present that entropy and cyclic universe cannot go together. But our main motivation was, in fact, to find the cyclic eternal universe that at the same time is physically viable. So the only way was to find a way how to escape from this BGV theorem and to find this eternal universe we want to present as an alternative to the CMB, lambda CMB theory. So this was one of the main motivations here.
Right. Okay. So, Petar, you claimed in the paper like it seemed like you had a more general problem with the whole entropy argument. You said something like the concept of entropy growth is highly questionable, and that was like in the intro to the paper. I was wondering if you could just unpack that a little bit.
Yeah, actually, the funny thing is that to some point, maybe all of this that we have been speaking maybe has no sense, so to say. I mean, it's half jokes, so to say. So why? Because actually, we are not very much convinced that at the present time it is meaningful to talk about entropy in the context of space-time, in the context of gravity. Why? Because actually and when I speak I think about the whole physical community, we don't know exactly how to deal with these things. We don't know exactly what is going on. We don't have the proper understanding of how to actually describe entropy evolution of a four-dimensional space-time of general sort, and we don't know what's the interplay between the gravity and entropy. Basically, the argument is if we don't know actually how to properly understand entropy in the context of the whole universe and gravity, then it's just not fair to use this argument against cyclic universe, because also we have problems with the standard Big Bang model and with the standard cosmological picture when we apply the concept of entropy to it. As we said before, you have the cosmic microwave background, and then it's actually almost a perfect fit, very good fit to the black body radiation spectrum. That means already in the very early universe, you were in the situation of thermal equilibrium. That means maximal entropy. And actually, Roger Penrose points this out and describes this very nicely. Then he proposes that there are additional degrees of entropy which are stored in the gravitational field and so on. But this is very hypothetical. I'm not convinced. I don't see that we can meaningfully now make any sort of construction that would describe entropy to gravitational degrees of freedom. And from a purely geometrical approach to gravity, in the same sense that we cannot actually then associate energy with the gravitational field as such. I don't actually believe in associating entropy with the gravitational field as such. But to put it short, I think essentially we don't know what's going on with entropy, gravity, even in the standard cosmology. We don't know if the concept of entropy can actually be meaningfully applied to the whole universe and its evolution. So we know that the concept of entropy plays a very important role in the thermodynamics, but this thermodynamical system is something very, very different from the universe in its totality, and we actually don't know the interplay of the evolution and various physical configurations which are possible are somehow influencing the whole story of entropy when we consider the cosmology. So starting from this argument, I think we should, actually restrain ourselves from talking too much about entropy in terms of cosmology, at least until we understand it better, no? But our argument was, okay, let's assume for the sake of the argument that the opponents are right, that you can meaningfully ascribe the notion of entropy to the whole universe. Let us assume this. And then we want to answer that still, if we assume that this can be meaningfully applied, the concept of entropy to cosmology, still it is not necessarily so that secret cosmologies are in contradiction with the principle of entropy growth. That was also the point.
Let me just ask you something that's just occurred to me. So Roger Penrose, his motivation for his cyclics, he's got a different cyclic scheme.
Yes.
Which is, well, we've got videos on this. You can go on our channel and watch them. And it's Big Bang as well. But his motivation is that, well, the entropy of the early universe was incredibly low, and it's not what you would expect. So it's claimed to be fine-tuned to 10 to the 10 to the 123 or something. Are you saying that claim of, and what he's saying is, therefore, the entropy wasn't set randomly. It must have been set by some mechanism, and his mechanism is his cyclic scheme. Are you saying that actually is not the case? That you can't say that the entropy is fine-tuned to this ridiculously high number because you can't define the entropy? Is that what?
It is not, logically, it is not necessarily so. This counting of entropy, discussion of entropy, saying that there is entropy in gravitational degrees of freedom, it is all basically hand-wavy. It is qualitative type of approximative argument, which is also hypothetical at the same time. So I don't think it is physically actually very convincing. It could be perhaps, but it is not that we need to take it as a fact now. But what I'm pointing to, that the problem which he focuses on, from which he starts, how come that CMB actually fits so well the broad body radiation spectrum? That's a very, very good
And
problem.
that's high entropy, right? The black body spectrum is super high entropy.
Yeah, yeah. So
Right.
that is, I think this is the problem is there, but his solution is one type of a hypothetical solution which is there, but it is not necessarily, and it's not the only one solution which
Right.
be there.
Right. Okay. Marko, have you presented this to your colleagues? Have you had any reaction? Your particular solution to the entropy problem?
So, and this is an interesting question. Yes, there were some reactions. As I know, some colleagues we know were very good reaction from them. They find it very interesting work, but also there are some very strange reactions that maybe this is all wrong, that that doesn't have any meaning. But for me here in Croatia, I am working in the University of Zagreb. There are not too many colleagues who are working in this with these problems. Croatia is a very small country, so maybe only our 5 or 10 here people are working in the cosmology in this concrete sense. So there are not too many reactions, but as I find somewhere outside this country, I find they're very colorful reactions. There are a lot of them who praise this work, but also a lot of them who find it that does not have any meaning. That the entropy always needs to be as they think it will be. Sometimes they don't. Their thinking is not too. I don't know how to express it. What?
I actually want to say, it's a bit, I think nowadays, it's a bit strange, the climate in the physical community. I think it's not maybe the same as people outside would think as it is. It's not like there is much discussions and confrontations going on, like the proponents of one theory are attacking the proponents of different theories and they somehow exchange the views. Basically, this is not happening so much. So mostly when you publish a paper like this, you will get some affirmative positive reaction. People will say it's great, nice to read and so on. But from the opposite part of the spectrum, it's more like people will not go into any type of a discussion. They will just not engage. It will just like they will just let it go by and they will just, even if you, for instance, fight there Vatican and say, like, we proven it was not so, people will say it is not how we meant, or try to somehow escape the discussion. So it's mostly this climate. People who like the idea and are doing similar research, they support you and say, yeah, it's great. And then you have the people who try to do opposite things, but they are not willing to have some sort of discussion or to answer with counter arguments, but it's more likely you will not react, let it just pass. As I say, it's a general climate nowadays, because I don't know, people are afraid of any type of confrontation, maybe for their surname prestige. So people try to be tough, somehow, very polite with each other, but to a very exaggerated level. In the sense that there is not enough of discussion and confrontations going on in the physical community. I think that's a big problem.
And sometimes people don't want to hear new ideas. I don't know why. When I present something new, they usually don't want to hear that. They want to work what they know, and that's it. There's no.
It's not the case. Yeah, people are publishing.
Right. So I want to finish off with experiments. So obviously your theory's defending a cyclic universe, and some of the motivation for your loophole is through modified gravity theories. Is there any way we could experimentally raise our credence that we do live in a cyclic universe, or that we do have one of these modified gravity theories? Petar, why don't you answer that?
Okay, so I see three main experimental verifications, but none of them are actually completely direct. It's more like the implications which are important. So first thing is experiments related to strong gravitational field, like black holes, for instance. Anything related to black hole physics is very significant because they would assume that there could be potential deviations from the standard Einstein's gravity, which we could detect in in these scenarios, in these regimes. And this is somehow necessary for consistent cyclic cosmology, that we go beyond standard Einstein's theory. And if we have some experimental signals of going beyond the standard Einstein's gravity, they can already constrain the possible mathematical territory in which these new theories can happen. So that can be very important if there is a modification which is manifested, and this modification is consistent with cyclic universe mathematically. That is one thing. Then the second thing is that we should somehow need to observe the time variation of the so-called dark energy, so that actually cosmological constant is not constant, because somehow you can view this dark energy as the mathematical object which measures the absence of our knowledge. So if this absence of our knowledge is just fixed, and you can somehow have a picture of the universe, the evolution of the universe by this constant term added to standard Einstein's equations, that means you don't have enough of dynamics to escape the singularity in the past. So one would assume.
And just want to interrupt 1 second. DESI, the dark energy spectroscopic instrument, has reported some about 4 sigma, so not quite enough to be
Yes.
sure, but they've reported about 4 sigma, actually variation in the cosmological constant. Could that be what you're talking about?
Yes, it could be, yes.
Mhm.
But it's now, of course, there are more papers actually claiming that the results are consistent with the variation of dark energy. So that cosmological constant is not actually constant, but it is not still significant enough, and we are not sure enough about these results. But I think that in the following years and decades, I'm quite convinced, that's my hypothesis, that it will be proven, that we will see that the data at some point will not, you could not fit them any longer in the paradigm of constant cosmological constant cosmological term.
Right, right.
The thing could be like to have some type of a signal coming to us from the previous contraction phase. And the only type of signal that could pass through the CMB and the very early universe too, that we know of, is the gravitational wave. So if we can detect the gravitational waves coming from the previous cycle, and that could have different shape than the inflationary gravitational waves, that would be one signal also of the cyclic universe. But also, like,
So would that be that inflation says it's a red spectrum, so more power at longer wavelengths, and the cyclic one would have a blue spectrum? Is that right?
but it is it was calculated in one specific model. So, but it's questionable how general this result is for all the possible cyclic models and different scenarios. I think there could be also models which would have almost indistinguishable spectrum from the inflationary. It is not necessarily following from the structure of cyclic kinematics itself that it needs to be different. It depends on the very specific model. That's not an easy question, I think. Then I think one type of indirect also proof for the cyclic cosmology could be that you have all these things which are combining and converging. For instance, you can explain the evolution perhaps without inflation. You don't have the singularity problem. You have some confirmed deviations in gravitational fields from the standard Einstein's equations. So all these things go together, and then you have a better, more consistent, and less pathological picture of the evolution of the universe given by cyclic model. So theoretically, that can also mean that it should be favored. So we don't now have this type of convergence at this time, but it is possible, and it would also signal its superiority in the future, I think, if something like this.
Well, we shall see. There's all kinds of exciting.
Yeah, we shall see. Yeah.
Whether we'll find a modification to gravity, whether we'll see this confirm the signal from DESI, or whether it will go away, we will see. So thank you so much, guys, for being on and explaining your paper. I'm sure the theoretical debate will go on. If you, the viewer, have any comments, please leave them in the comments. And if you like this content, please like and subscribe, and we'll see you next time. Thanks, guys.
Thank you so much. Thanks for inviting us. Yeah. All the best. Thank you.